In this question, we have a neutral copper atom, and we're trying to find out its electron configuration. So let's head to the periodic table and find copper. And here it is. Copper is here. It's one of the transition metals, and it has an atomic number of 29, meaning 29 protons, and therefore 29 electrons in a neutral atom. So 29 electrons in a neutral copper atom. We're trying to find the ground state electron configuration. So same as usual, let's draw out our little table that we use with all our energy sublevels shown. And this goes on with 6 and 7, but we're going to stop here for now. And same as always, we use these diagonal arrows drawn through here to show which ones get filled first as a helpful reminder, since the order doesn't just follow the rows. Okay, so let's figure out our electron configuration for copper. So first we're going to fill the 1s subshell. So that'll be 1s. Remember, s can fit up to 2 electrons, so it'll be 1s2. 2s can also fit up to 2 electrons, so that'll be 2s2. 2p can fit up to 6 electrons, so that'll be 2p6. So far we've used up 10 of our 29 electrons, so we've still got 19 to go. 3s can fit up to 2 electrons, so that'll be 3s2. Next we have 3p, that can fit up to 6 electrons, that's 3p6. Okay, so far we've used 18 electrons. We need to get to 29, so we still have 11 electrons to add. Next we have 4s. So according to our rules so far, we would fill that one first and we'd have 4s2. And then lastly we'd have 3d. We've got 20 electrons filled up so far with 9 left, so that would leave us with 3d9. So this is what we would expect based on the rules we've used so far. However, there are some exceptions to these rules. Copper is one of the examples of something with an exception. And the exception often comes up when we have a situation where our d orbital would be nearly full. So it's got 9 here. To be full, it would have 10. That would make it really stable. Now, it turns out that what would be more stable than having a full s orbital and a partially full d orbital, it will be more stable to actually have a partially full s orbital and a full d orbital. So in this example, instead of following the rules we've used so far, one of the electrons from the 4s2 orbital actually goes into the 3d orbital. So we actually end up with 4s1 and 3d10 as our electron configuration here. So let's fill that out here. We've got 1s2, 2s2, 2p6, 3s2, 3p6. Next, instead of 4s2 as we might expect, it's actually 4s1. And instead of 3d9 as we might expect, it's actually 3d10. And the rest of these are empty here. The other common place where we find this is a situation where instead of having a full 4s shell and a partially full with 9 3d shell, it also happens where we have a 3d shell that has 4 electrons. It turns out that instead of having 2 electrons in the 4s and 4 in the 3d, it's actually more stable to have 1 electron in the 4s and 5 electrons in the 3d. If you picture what that looks like, the d subshell has 5 orbitals in it. So this is saying that it would rather have 1 in all of those orbitals, so that overall the d subshell is half full, and 1 in the 4s. This would actually be more stable than having the 4s be full and the 3d only have 4 electrons and not even be half full. So these are just some exceptions that you need to learn that don't follow the rules that we followed so far.